Hi, I am SHARAVAIAH, lecturer in mathematics from MVS Degree College, MAHABOOBNAGAR. Today we are discussed some problems of a Riemann integration. First one, computer find out integration 0 to 9 integral part of root t dt or integration 0 to 9 integral part of root x dx. Integral part of root x dx integration limits are 0 to 2. That is, we are given that it is comparing to the given integral integration a to b f of x dx equal to integration 0 to 9 root x integral part of root x dx. Given that integration a to b f of x dx equal to integration 0 to 9 integral part of root x dx, where f of x equal to integral part of root x, where integral part of root x mean greatest integer function. That is, there exists a unique integer n belongs to z such that n less than or equal to x less than n plus 1. That implies integral part of x equal to n. Already we know that by definition of integral part of x, where integral part of root x, where we have to find out the where x values are f of x function value are integral part of root x on the interval x belongs to closed interval 0, 9, where once we observe that where root of 0 equal to 0, root 1 equal to 1, root 2 equal to 1.414, root 3 equal to 1.732, next one root 4 equal to 2, root 5 equal to 2.236, root 6 equal to 2.449, root 7 equal to 2.645, root 8 equal to 2.828, root 9 equal to 3. Then first one we have to where we have defined the function f of x on interval closed interval 0, 9. Therefore first one f of x equal to where integral part of, suppose where now we consider it can be divided by the some subintervals 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. Okay. First one where f of x equal to integral part of x, integral part of root x, 0 less than or equal to x less than 1. That is where we substitute x value 0 and between the 0 to 1 any real number. That implies integral part of root 0 equal to 0, integral part of root 0.9, it is also something lies between 0 to 1. Therefore integral part of roots where integral part of root x where x value lies between 0 and between 0 to 1 it is equal to 0. Next one where x values are lies between 1 to 2. Suppose root 1 equal to 1. Therefore 1 it is the lies between the two integers 1, 2. Therefore integral part of 1 equal to 1. Suppose where we substitute x value 1.99 something, 1.999 something, it is also the root it is equal to 1 point something value. Therefore integral root of 1.99 something, it is must be less than 1, 2. Therefore integral part of root x equal to 1 less than or equal to x less than 2. Similarly where x values are lies between 2 or 2 to 3. Therefore where suppose put x equal to, that implies root 2, where root 2 equal to 1.414, where 1.414 it is lies between the two integers 1, 2, 1 less than 1.414 less than 2. That implies integral part of 1.414 equal to 2. That is integral part of root 2 equal to. Similarly where we substitute x value less than 3 mean 2.99 something, it is also 1.55 something, therefore 1.66 something. Therefore integral part of root of 2.99 it is lies between the two integers 1, 2. Therefore integral part of root 2.99 something, that is equal to 1. Similarly where we substitute x value are 3 to 4. Therefore suppose 3 equal to root 3 equal to 1.732. 1.732 it is also lies between the two integers 1, 2. Therefore integral part of root 3 equal to integral part of 1.732 equal to integral part of 1.732 equal to 1. Suppose where x value are 3.99 something, it is where root of 3.99 something equal to 1.99 something, 1.99 something, integral part of 1.99, it is lies between the 1 comma 2, therefore integral part of root x equal to 1, where x value is 3 or lies between 3 comma 4, therefore x value lies between 0 less than or equal to x less than 1, integral part of root x equal to 0, 1 less than or equal to x less than 2, integral part of root x equal to 1, 2 less than or equal to x less than 3, integral part of root x equal to 1, 3 less than or equal to x less than 4, integral part of x root x equal to 1. Similarly, where we substitute x values are 4 less than or equal to x less than 5. Suppose x equal to 4, that implies root 4. Root 4 equal to 2. Therefore, 2 it is the integer. Therefore, integral part of 2 equal to. Similarly, where x less than 5 mean 4.999 something, it is must be 2.0 something, 2.12 something. Therefore, it is also lies between the two integers 2 comma 3. Therefore, integral part of root x equal to 2, x value it is lies between 4 less than or equal to x less than 5. Similarly, 5 less than or equal to x less than 6, where root 5 equal to 2.236. Suppose x equal to 5, root 5 equal to, where root 5 equal to 2.236, therefore integral part of 2.236 equal to automatically 2. It is lies between the two integers 2 comma 3. Therefore, 5 less than or equal to x less than 6, that implies integral part of root x equal to 6 less than or equal to x less than 7. Therefore, where root 6 equal to 2.4449. Therefore, integral part of root 6 equal to integral part of 2.449 equal to 2. Therefore, x value is lies between the 6 less than or equal to x less than 7. Therefore, automatically integral part of root x equal to. Similarly, 7 less than or equal to x less than 8. 7 less than or equal to x less than 8, where root 7 equal to 2.645. That implies root 7 equal to integral part of root 7 equal to integral part of 2.645 equal to 2. Therefore, where x value is lies between the 7 less than or equal to x less than 8. Similarly, 7.99 something, it is also lies between 2.8 something. Therefore, 7 less than or equal to x less than 8 implies it is equal integral part of root x equal to 8 less than or equal to x less than 9. Therefore, where root 8 equal to 2.828, 2.828 it is also lies between the 2 comma 3, where x is less than n, that implies x less than n mean where x value is 8.99 something, it is also where the root of 8.99 something is equal to 2.99 something, 2.99 something, it is lies between the two integers 2 comma 3, that implies integral part of root x equal to. Therefore, f of x equal to integral part of root x on closed interval 0 comma 9, it can be defined as where on the interval 0 less than or equal to x less than 1 0, 1 less than or equal to x less than 2 1, next one 2 less than or equal to x less than 3 1, 1 such that 3 less than or equal to x less than 4, 2 such that 4 less than or equal to x less than 5, 2 such that 5 less than or equal to x less than 6, next one 2 such that 6 less than or equal to x less than 7, next one 2 such that 7 less than or equal to x less than 8, next one 2 such that 8 less than or equal to x less than 8. Very clearly we observe that f of x equal to root of integral part of x is a piecewise continuous function on closed interval 0 comma 9. Therefore, we can define as if f of x equal to integral part of root x on closed interval 0 comma 9. Therefore, that implies f of x is a piecewise continuous function of closed interval 0 comma. Already we know that by previous theorem, every piecewise continuous function on closed interval a comma b or every bounded piecewise monotonic function on closed interval a comma b, it is must be Riemann integrable. Therefore, where f of x is a piecewise continuous function on closed interval 0 comma 9, that implies f of x is Riemann integrable on closed interval 0 comma 9, and the integration value and integration 0 to 9 f of x dx equal to, it can be divided by the subinterval 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9. Therefore, integration 0 to 9 f of x dx equal to integration 0 to 1 f of x dx plus integration 1 to 2 f of x dx plus integration 2 to 3 f of x dx plus integration 3 to 4 f of x dx plus integration 4 to 5 f of x dx plus integration 5 to 6 f of x dx plus integration 6 to 7 f of x dx plus integration 7 to 8 f of x dx plus integration 8 to 9 f of x dx, where already where the function f of x it is defined as on integration 0 to 1 0, 1 to 2 1, 2 to 3 1, next one 3 to 4 1, 4 to 5 2, next one 5 to 6 to 526 to 627 to 728 to 829 2. Therefore, on the interval 0, 1, it is where f of x equals 0 on the subinterval, on the open subinterval 1, 2, 1, 2, 3, 1, 3, 3 to 4, 3, 4, 1, 4 to 5, 2, 5 to 6. Therefore, we substitute all the values. Therefore, integration 0 to 1, 0 dx automatically 0. Integration 1 to 1 dx mean x limits are 1 to 2. Integration 2 to 3 dx also x 2 to 3. Integration 3 to 4 x automatically limits are 3 to 4. Integration 4 to 5 2 into dx mean 2 into x limits are 4 to 5. Integration 5 to 6 dx mean 2 into x limits are 6 to 7. Integration 6 to 7 2 dx equal 2 into 6 to 7. Integration 7 to 8 2 into dx mean 2 into x 7 to 8. Integration 8 to 9 2 into dx equal to x 8 to 9. Therefore, substitute upper and lower limits. First one 2 minus 1. Second one 3 minus 2. 4 minus 3. 2 into 5 minus 4 equal to 1. Next one 2 into 6 minus 5 equal to 1. 2 into 7 minus 6 equal to 1. 2 into 8 minus 1 equal to also 1. 2, 3, 4, 5. Therefore, 1, 1, 1. Next 2, 2, 2. That implies totally adding 1 plus 1 plus 2 plus 2 plus that equal to 13. Therefore, integration 0 to 9 integral part of root t into dt or integration 0 to 9 integral part of root x dx it is value must be equal to 13. That is using by the piecewise continuous function. Next problem, show that the function f of x is defined as f of x equal to x such that x is an integer. Second one, f of x equal to 1 such that x is otherwise mean x is not integer mean x is the for all a belongs to r minus z is integrable on closed interval 0, n where m being a positive integer, that is m value lies between 1, 0, 1, m value is 1, 2, 3, 4 up to dash up to so on. Therefore, where is integrable mean where we have to verify that the function f of x is not integrable, it is Riemann integrable or not. F of x is Riemann integrable or not on the interval closed interval 0, 1, that is m equal to 1 or 2 or 3 or 4 up to dash. Where given that the function f of x it is defined as on the closed interval 0, 1. Suppose where now we let m equal to 1. Therefore, the interval 0 to 1, m equal to 0 to 2, m equal to 3, 0 to 3, m equal to 4, 0 to 4, m equal to 100, 0 to 100 up to so on. Where given that f of x equal to 0 such that x is an integer. X is an integer mean x value it is lies between 0, 1, 2, 3, 4 up to so on m. X belongs to closed interval 0, m and x is must to be integer, that is x equal to 0, 1, 2, 3, 4 up to so on. Second one 1 otherwise mean x belongs to closed interval 0, 1 it is not integer, that is it is real number, that is x for all a belongs to r minus z, that is where f of x equal to 1 such that r minus 1 less than x less than r, where x value it is the lies between r minus 1 r, where r is a integer, r equal to 1, 2, 3, 4 up to so on m. Suppose where we substitute r equal to 1, that implies it is the 0 less than x less than 1. Suppose where we substitute x equal, that is where x value lies between 0 to 1 any real number, that implies the value must it is rational or irrational number, it is equal to 1. Suppose r equal to 2, that implies r equal to mean that implies 2 minus 1 less than x less than 2, that implies 1 less than x then, where x value it is any real number between 1, 2, the image is must be equal to 1. Therefore, where the function f of x is defined as on any x value it is integer on the interval 0, m where the image it is equal to 0, where x value it is belongs to on the interval 0, m except integer, the image it is must be equal to 1. Therefore, given that the function f of x is defined as f of x equal to 0 such that x is an integer, that is x equal to 0, 1, 2, 3 up to so on m, 1 such that r minus 1 less than x less than r equal to except integers. Okay, that implies we clearly observe that where the function f of x has the images are lies between only 0 to 1. That implies 0 less than or equal to f of x less than or equal to 1 for all x belongs to closed interval 0 comma m. That implies f of x is bounded function on closed interval 0 comma m. By definition of bounded function, there exists a real number k1 less than or equal to k1 comma k2 belongs to R such that k1 less than or equal to f of x less than or equal to k2 for all x belongs to interval a comma b. That implies f of x is bounded. That implies f of x is bounded on closed interval 0 comma m. And very clearly we observe that the function f of x is not continuous on any integer it is belongs to 0 comma m. That and where f of x is not continuous only at integers, only at x equal to 0 comma 1 comma 2 comma 3. That is f of x is continuous for all x belongs to r minus z. That is f of x is continuous, f of x is a continuous on every real number except integers. That is 0.1, 0.2, 0.3, 1.1, 1.2, 1.3, 2.9, 3.4. The function f of x is continuous. F of x is not continuous at integer. It is continuous on for all x belongs to r minus z. That implies where f is a bounded on closed to 0 comma m and f has only m plus 1 points. That is suppose where m value 100. Therefore x is not continuous at 0, 1, 2, 3, 4 up to so on 100. There are totally 101 points. Therefore suppose where m equal to 50, therefore f of x is not continuous at x equal 0, 1, 2, 3 up to so on 50. Therefore where 51 points. Therefore f of x is not continuous at only 51 points. That implies where f is bounded on closed interval 0 comma m and f has only m plus 1 points of finite points of discontinuities. That is f has a only finite number of discontinuity points. Finite number of discontinuity points, that is 0 comma 1 comma 2 comma up to so on m. F is bounded on 0 comma m and f has only m plus 1 points mean finite number of points of discontinuities 0 comma 1 comma 2 comma 3 comma up to so on m. By previous theorem already we know that by previous theorem f is a bounded on closed interval a comma b and f has finite number of discontinuity points on closed interval a comma b, then f is Riemann integrable. Already we know that by previous theorem f is a bounded function on closed interval a comma b and f has a finite number of points of discontinuities on closed interval a comma b, then f is Riemann integrable. Where f is a bounded function on closed interval 0 comma m and f has a finite number of discontinuities 0 comma 1 comma 2 comma 3 comma up to so on m on closed interval 0 comma m. That implies f is Riemann integrable on closed interval 0 comma m. F is Riemann integrable on closed interval 0 comma m. Therefore the integrand value integration 0 to m f of x dx equal to integration 0 to 1 f of x dx, integration 1 to 2 f of x dx up to direct integration m minus 1 to m f of x dx. Where already we know that where the function f of x is defined as any subinterval where it is lies between the x value lies between 0 to 1, 1 to 2, 2 to 3, m minus 1 to m except integer where the image must be equal to 1. That implies integration 0 to 1 where f of x equal to 1, integration 1 to 2 1, integration 2 to 3 1, also integration m minus 1 to m 1 except all integers the image must be equal to 1. Therefore it is integration 0 to 1 1 dx, 1 to 2 1 dx, 2 to 3 1 up to so on m minus 1 to m dx. That is x limits are 0 to 1, x 2 to 1 to 2 up to so on x m minus 1 to m. Therefore 1 minus 0, 2 minus 1, 3 minus 1, 4 minus 1 up to so on m minus 1, that is m minus m plus 1, that is 1 1 1 1 up to so on m times that equal to m. Therefore f is Riemann integrable on closed interval 0, m. That implies integration 0 to m f of x dx equal to m. Suppose we m equal to 100, therefore integration 0 to 100 f of x dx equal to 100. Suppose x equal to 2020, integration 0 to 2020 f of x dx equal to 2020, where m is any positive integer. Therefore the function f of x is defined as f of x equal to 0 such that x is an integer, 1 such that otherwise. Therefore f is Riemann integrable on closed interval 0, m and integration 0 to m f of x dx equal to m. Next, third one, show that the function f of x is defined as f of x equal to 1 by 2 to the power of n such that 1 by 2 to the power of n plus 1 less than x less than or equal to 1 by 2 to the power of n, where n equal to 0, 1, 2, 3 up to so on. F of 0 equal to 0 is integrable on closed interval 0, 1 and integration 0 to 1 f of x dx equal to 2 by 3. Okay, we are given that the function f of x is defined as f of x equal to 1 by 2 to the power of n such that 1 by 2 to the power of n plus 1 less than x less than or equal to 1 by 2 to the power of n. Therefore f of x equal to 1 by 2 to the power of n such that 1 by 2 to the power of n plus 1 less than x less than or equal to 1 by 2 to the power of n equal to 0, 1, 2, 3. Next 0 such that x equal to 0, where we substitute n equal to 0. That implies 1 by 2 to the power of 0 equal to 1. 1 by 2 to the power of 0 plus 1, 1 by 2 less than x less than or equal to 1 by 2 to the power of 0 equal to 1. That implies x value it is less between 1 by 2 less than x less than or equal to 1. That implies where image f of x equal to 1. Similarly substitute n equal to 1. That implies 1 by 2 to the power of n equal to 1 by 2. 1 by 2 to the power of 1 plus 1 mean 1 by 2 square less than x less than or equal to 1 by 2 square, 1 by 2 x equal where n equal to 1. Similarly n equal to, that implies 1 by 2 square. 1 by 2 square mean 1 by 2 to the power of 2 plus 1, 1 by 2 cube less than x less than or equal to 1 by 2 square up to dash 1 by 2 to the power of n minus 1 such that 1 by 2 to the power of n less than x less than or equal to 1 by 2 to the power of n minus 1, 0 such that x equal to 0. Therefore where f of x equal to 1 such that 1 by 2 less than x less than or equal to 1, 1 by 2 such that 1 by 2 square less than x less than or equal to 1 by 2, 1 by 2 square such that 1 by 2 cube less than x less than or equal to 1 by 2 square, 1 by 2 to the power of n minus 1 such that 1 by 2 to the power of n less than x less than or equal to 1 by 2 power 0 such that x equal to 0. Where clearly we observe that f of x is a bounded function where the images are lies between 0 to 1, 0 less than or equal to f of x less than or equal to 1, 1 by 2 less than 1, 1 by 2 square less than 1 greater than 0. Therefore f of x is bounded on closed interval 0, 1 and where f of x is not continuous at x equal to 0, 1 by 2, 1 by 2 square, 1 by 2 cube, 1 by 2 to the power of 4 up to dash 1 by 2 to the power of n minus 1 such that n belongs to n. That is f of x has a infinite number of points of discontinuities on closed interval 0, 1, where that implies f of x is bounded on closed interval 0, 1 and f of x is not continuous at only x equal to 0, 1 by 2, 1 by 2 square, 1 by 2 cube, up to that is f of x has a infinite number of points of discontinuity and f of x is continuous at infinite number of points. F of x is continuous at infinite number of points, f of x is discontinuous infinite number of points, where f of x is not continuous at x equal to 0, 1 by 2, 1 by 2 square, 1 by up to dash on going to 0, 1, where the set of points of discontinuity of f of x on closed interval 0, 1 is the set of points of discontinuity of f of x on closed interval 0, 1 is set of 0, 1 by 2, 1 by 2 square, 1 by 2 cube up to dash has, but where the set of points of discontinuity of f of x on closed interval 0, 1 is infinite, but limit point is u only, but limit point is finite. That is where the set of all infinite number of points of discontinuity has only one limit point, that is equal to 0. Therefore where f of x is a bounded function on closed interval 0, 1 and the set of points of discontinuity points are infinite, but it has only one limit point. Therefore by previous theorem therefore by previous theorem already we know that f is bounded function on closed interval 0, 1, f has a infinite number of points of discontinuities on closed interval a, b, but it has finite number of limit points, where f is a bounded on closed interval 0, b, 0, 1. It has infinite number of points of discontinuity, but it has only one limit point mean it has a finite number of limit points. That implies by previous theorem we know that f is Riemann integrable on closed interval a comma b. What is by previous theorem? F is bounded on closed interval a comma b. F has a infinite number of points of discontinuity on closed interval a comma b, but it has finite number of limit points on closed interval a comma b. Then f is Riemann integrable on closed interval a comma b. Therefore, by previous theorem we get f is Riemann integrable on closed interval 0, 1, and the integration value integration 0 to 1 f of x dx equal to, it can be divided as a subinterval where 1 by 2 to 1, 1 by 2 square to 1 by 2, 1 by 2 cube to 1 by 2 square, 1 by 2 power of 1 to 1 by 2 to power of n minus 1. Integration 0 to 1 f of x dx equal to integration 1 by 2 to 1 f of x dx plus integration 1 by 2 square to 1 by 2 f of x dx plus integration 1 by 2 cube to 1 by 2 square f of x dx up to, so integration 1 by 2 to the power of n into 1 by 2 to the power of n minus 1 f of x dx. Therefore, integration 1 by 2 to 1 f of x dx equal to where 1 already we know that 1 by 2 to 1 the limit are 1, 1 by 2, 1 by 2 square, 1 by 2 power of n minus up to so on. Therefore, 1 by 2 to 1, 1, 1 by 2 square to 1, 1 by 2 square to 1 by 2 f of x dx mean 1 by 2, 1 by 2 cube to 1 by 2 square, the function f of x equal to 1 by 2 square up to so on. 1 by 2 to the power of n to 1 by 2 to the power of n minus 1, the function f of x equal to 1 by 2 to the power of n minus 1. Therefore, integration 1 by 2 to 1 dx mean x limits are 1 by 2 to 1. Similarly, 1 by 2 into x limits are 1 by 2 square to 1 by 2. Next one, 1 by 2 square into x limits are 1 by 2 cube to 1 by 2 square up to so on. 1 by 2 to the power of n minus 1 into x limits are 1 by 2 to the power of n to 1 by 2 to the power of n minus 1. I clearly observe that substitute upper and lower limits x 1 minus 1 by 2. Second one, 1 by 2 into upper limit 1 by 2, lower limit 1 by 2 square, 1 by 2 minus 1 by 2 square, where plus 1 by 2 square into upper limit 1 by 2 square, lower limit is 1 by 2 cube, 1 by 2 square minus 1 by 2 cube. Similarly, up to so on, 1 by 2 to the power of n minus 1 into upper limit 1 by 2 to the power of n minus 1, lower limit 1 by 2 to the power of n, 1 by 2 to the power of n minus 1 minus 1 by 2 to the power of n. Therefore, 1 minus 1 by 2 equal to 1 by 2, where plus 1 by 2 into 1 by 2 minus 1 by 2 square, 1 by 2 minus 1 by 4, LCM 4, therefore 2 minus 1 by 4, that equal to 1 by 4, 1 by 4 mean 1 by 2 square, that is 1 by 2 into 1 by 2 square, plus 1 by 2 square into 1 by 2 square equal to 1 by 4, 1 by 2 cube equal to 1 by 8, 1 by 4 minus 1 by 8, LCM is 8, therefore 2 minus 1 by 8, that equal to 2 minus 1 by 8 mean 1 by 8, that equal to 1 by 2 cube, that is 1 by 2 square 1 by, where we observe that 1 by 2 plus 1 by 2 into 1 by 2 square, 1 by 2 square into 1 by 2 cube up to dash orderly 1 by 2 square 1 by 2 cube, 1 by 2 1 by 2 square, 1 by 2 to the power of n minus 1 into 1 by 2 to the power of n. That implies taken 1 by 2 is common each and every term, 1 by 2 into first one 1 plus second one 1 by 2 square, third one where 1 by 2 is common, 1 by 2 into 1 by 2 cube, 1 by 2 to the power of 4, that is 1 by 2 square whole square plus up to so on 1 by 2 square whole to the power of n minus 1, 1 by 2 square, 1 by 2 square whole square, 1 by 2 square whole to the power of n minus 1, where we observe that it is the where the bracket one is, it is the geometric series where a equal to 1 or equal to 1 by 2. Therefore, where the in terms of the sum of in terms of the geometric series is a into 1 minus r to the power of n by 1 minus r, where r equal to 1 by 2 it is less than 1. Suppose r greater than 1, a into r to the power of n minus 1 by r minus 1, where r is 1 by 2 it is less than 1, that implies 1 by 2 into a mean 1, therefore 1 minus r to the power of n, 1 minus 1 where r mean 1 by 2 square, that implies 1 minus 1 by 2 square over to the power of n by 1 minus 1 by 2 square, where r equal to 1 by 2 square, 1 by 2 square, 1 by 2 square whole square, 1 by 2 square, that is up to dash. Therefore, a into 1 minus r to the power of n by 1 minus r, that is 1 minus 1 by 2 square mean 1 by 4, 1 by 4 over to the power of 1 mean 1 by 4 to the power of n, that is by 1 minus 1 by 2 square mean 1 minus 1 by 4, that equal to 1 minus 1 by 4 equal 3 by 4, 3 by 4 can be written as in a numerator 4 by 3, that is 1 by 2 into 4 by 3 equal to 1 minus 1 by 4 to the power of n, that equal to 2 by 3 into 1 minus 1 by 4 to the power of n. Taken n tends to infinity, integration 0 to 1 f of x dx equal to limit n tends to infinity 2 by 3 into 1 minus 1 by 4 to the power of n. Substitute n equal to infinity, that implies something by infinity, that equal to 0. Therefore 2 by 3 into 1 minus 1 by infinity, that is 2 by 3 into 1, that equal to 2. Therefore integration 0 to 1 f of x dx equal to 2 by 3. Therefore the function f of x is defined as f of x equal to 1 by 2 to the power of n such that 1 by 2 to the power of n plus 1 less than x less than equal to 1 by 2 to the power of n such that n equal to 0, 1, 2, 3 up to 1 f of 0 equal to 0. Therefore the function f of x is Riemann integrable or integrable on closed interval 0, 1 and integration 0 to 1 f of x dx equal to 2 by 3. Thank you.